CPU cache efficiency. How to measure what you can't see. Hello and welcome to episode number 19 of the Unity Performance Task Force podcast. I'm your host, Ruben from TheGameDev.Guru, and as usual, I'll kick things off with a question for you. Have you ever wondered why some of your scripts run fast while others crawl, even when they're doing similar work? The answer might be hiding in a place most Unity developers never look: your CPU cache. Here's a number that should wake you up. Accessing data from RAM instead of your CPU cache costs you at least 100 times more. 100 times. That's not a typo. We're talking memory latency, we're talking power efficiency, we're talking about a performance gap so massive that ignoring it is like choosing to walk when you could teleport. So what does it mean to be cache efficient? Simple. It means retrieving as much data as you can from the cache instead of making that expensive trip to RAM. And yes, this applies to CPU caches, GPU caches, texture caches, any cache in general. When you get a cache hit, it means the CPU requested some data to run your scripts and found it right there in the cache. No expensive round trip to RAM, just grab and go. That's a win for performance and a win for battery life. Your players will thank you. Now let's talk about what the cache actually is. Your CPU cache is usually split into two parts. First, the instruction cache, where you store the operations the CPU is likely to execute next. Second, the data cache, where you keep the actual information needed to perform those operations. Instructions are what you do. Data is what you work with. If the data you need isn't in the cache, the CPU has to trudge all the way to RAM to fetch it. And that's where the 100x penalty comes in. Here's an analogy. Imagine you're studying calculus at home. You've got your main textbook right on your desk. That's your L1 cache, the fastest, smallest memory tier. When you need a formula, you just reach over and grab it. Done. But maybe you need a geometry reference. That book is on the shelf behind you. You stand up, walk over, grab it, walk back. That's your L2 cache. Bigger capacity, but slightly slower. Now let's say you want to study geology. That book isn't at home. It's at the library 20 minutes away. You have to drive there, present your ID, maybe pay a fee. That's RAM. Slow, expensive, and power hungry. The closer your data is, the faster and cheaper it is to access. That's the memory hierarchy in a nutshell. So here's the two-step plan. First, measure your cache efficiency. Second, optimize it. This episode is all about step 1, measurement. Fair warning, this is platform-specific territory. The same tools won't work everywhere. I'm going to show you how to do this on desktop with AMD, but if you're on Intel, you'll use Intel VTune. If you're on ARM, you'll need different tools entirely. Low-level profiling is a niche game, and the tooling reflects that. Let's define cache efficiency properly. One way to think about it is the ratio of cache hits to total cache accesses. If you hit 100% of the time, you never touch RAM. That's impossible in practice because cache is tiny, but that's the ideal. So how do we measure it? On Intel, use Intel VTune. It's free. You'll see metrics like load and store instructions, plus cache miscounts for specific functions. I'll link resources at the end. On AMD, use AMD uProf. That's what I'm using today with my Ryzen CPU. You can also try Visual Studio's profiling tools, though results vary. And if you're feeling adventurous, hardware emulators let you simulate how code runs on specific architectures. Let me walk you through a real test. I built a simple Unity scene. Pink background, one game object, with a script that accesses a giant array. The script has a Boolean toggle. If it's false, the script accesses array elements sequentially. If it's true, it accesses them randomly. Why does this matter? When you access data sequentially, the CPU fetches entire cache lines from RAM, not just single elements. It's like grabbing a whole box instead of one item. The next few elements you need are already sitting in cache waiting for you. Random access destroys this pattern. Every request is a surprise. The CPU can't predict what you need next, so it constantly fetches new data from RAM. More misses. Worse efficiency. I made 2 builds, one sequential, one random. Then I profiled both with AMD uProf. Here's the workflow. Open uProf as administrator, just when you need elevated permissions for this. Select your target application. Set core affinity to 0 to lock it to one CPU core for consistent results. Then add all the cache-related counters you want to track. L1 data cache misses, L2 cache misses, the works. Click Start Profile. Let it run for 7 seconds. Stop. Analyze. The metrics tell the story. In the sequential build, I had 89 L2 cache misses out of 188 total accesses. That's a 47% miss rate. In the random build, I had 203 misses out of 315 accesses. That's 64%. The random version is objectively worse at keeping data in cache. The numbers don't lie. Now, I kept this test short to show you the process. In a real optimization scenario, you'd run longer tests, isolate the exact code path you're improving, and remove as much randomness as possible. You want a clean comparison between your baseline and your optimized version. The worst case scenario? Profiling a chaotic multiplayer match where players are shooting at random times, triggering different scripts, executing unpredictable workloads. The results would be garbage. You can't compare noise to noise. Instead, build 2 versions of your game that execute only the specific operation you're optimizing. Loop it thousands of times, make that the only thing happening. Then measure. This is the exact checklist we use at TheGameDev.Guru when teams need to validate low-level optimizations. So when should you actually do this? If you're just using Unity features out of the box and not writing much custom code, this probably isn't worth your time. Even if you discover Unity has poor cache efficiency in some area, what are you going to do about it? Not much. But if your scripts take 30% or more of your frame time, and you have control over how those scripts access memory, then yes, measuring cache efficiency pays off. You can baseline your current approach, refactor for cache-friendly patterns, rebuild, and see if the numbers improve. This episode covered the measurement side. The next step is learning how to actually improve cache efficiency. We'll cover that in future lessons. Before we wrap up, here's a bonus insight. This is also why texture compression matters so much on the GPU. GPUs have texture caches, just like CPUs have data caches. When you compress your textures, they're more likely to stay in the texture cache instead of forcing a fetch from VRAM. Same principle, different hardware. 3 big takeaways. First, cache hits are 100 times faster than RAM access. That gap is massive. Second, sequential memory access is almost always more cache-friendly than random access. Third, you can measure cache efficiency with platform-specific tools like AMD uProf or Intel VTune, but only when you control the code and can isolate clean test scenarios. Most developers never go this deep, but now you know how. If you found this podcast episode useful, you can access in-depth lessons in the Unity Performance Task Force program at www.performancetaskforce.com. And if Unity consulting is what you are after, book a free discovery call at https://consulting.thegamedev.guru. Till next time.